We're now going to return to our study of finding formulas for antiderivative functions rather than graphical tools to estimate those graphs. And we're going to start off fairly simply, just using our intuition about differentiation to inform our techniques of antiderivatives or antidifferentiation. Let's take a look. So if we are looking for the integral indefinite, so we're looking for the antiderivative of cos 3x with respect to x, what will that look like? Well, let's remind ourselves of the sequence here. Whatever function we put as the answer here, and we might say, you know, cos of, oh, it wouldn't be cos, would it? It would be sine. Let's say sine of 3x. We can always check it by differentiating. So here we're integrating, or anti-differentiating. I'm just going to start calling it integrating from now on most of the time. We should be able to go back and get our cos of 3x back by taking that same function and differentiating it. Okay, so if our claim is, our guess is, that when we integrate cos 3x, we get sine 3x, we can check by differentiating. And we check and we get absolutely the derivative of sine is cos. Derivative of sine anything is cos of 3, the same thing, times the derivative of the inside, though. Now that's a problem because it's not equal to cos of 3x. It's 3 times cos of 3x. Fortunately, little issues like that can be fixed pretty easily. We just say, well, what if I had a third in there? If I had a third in there, then we would get back to our cos of 3x, exactly what we started with. These are equal now, and so we have the correct antiderivative. Let's put that 1/3 in there as well. So I'm integrating cos 3x. I guess sine 3x. It's a good guess, but it turns out we need to tweak it a little bit by adding a third. So we add the third, we check it. When we differentiate, the 3's cancel. We get back to just the cos of 3x that we want. And so we have the correct antiderivative. Last but not least, we also include a plus c because all this work about differentiation works out both ways, whether the c's there or not. And the indefinite integral is the most general antiderivative, so it includes the plus c constant there. What about e to the 3x minus 2 if we integrate that? Let's do the same technique. Our basic guess would be that while I differentiate exponentials, I get the same exponentials back. So we might expect that that would be our integral, maybe with a plus c, and that's our integration. And then we're going to check. We're going to take the derivative of what we just said there, e to the 3x minus 2 plus a constant, and we'll differentiate that. When we differentiate that, we get e to the 3x minus 2 again, of course. The derivative of e to the anything is e to the same thing, times the derivative of the exponent, though, and that'll give us a 3. So in fact, exactly in the same scenario that we had in the last case, we have an extra 3. We don't want the 3. Well, I can multiply things by scalars, and it won't change the derivative calculation. When we differentiate 1/3 e to the 3x minus 2 plus c, we're going to get this, and then we cancel those 3's, we'll get e to the 3x minus 2, and once again, we're back to equality here. I integrate e to the 3x minus 2, I get this. I differentiate this, I get back to e to the 3x minus 2, and that's our check that our integral value is correct. Now, sometimes it'll get a little more complicated. Inside this exponential, we have something that's not as easy to differentiate, or leads to a more complicated derivative term. We have e to the negative x squared. Fortunately, there's going to be an x here. So let's check how this might work. If we integrate, we might expect that we're going to see e to the negative x squared plus a constant. And again, we're going to do that same thing. That'll be our integration from this direction. And then we're going to differentiate it, e to the negative x squared plus c. And that will equal, going this way, that will equal e to the negative x squared times negative 2x. Well, we actually have in our integral value here the x, so that's perfect. In fact, the only thing we're off by is a constant of negative 1/2. So we just add a negative 1/2 everywhere, and then moving again right to left on this line, we'll end up with negative negative 2 x e to the x squared. Negative still there. These are equal, and so we get a check mark. This must be the antiderivative of x e to the negative x squared. Notice how crucial it was that this integral, though, be somewhat complicated, that it actually have this x along with the e to the negative x squared. And the reason we need that is that the derivative of e to the negative x squared triggers a chain rule. And the chain rule, which spits out the derivative of the x squared here, it produces an extra x on the main line of our function. So, or on the product or the numerator, we get an extra x out front. If we didn't have this x out front, we'd get an extra x in our derivative, and there's no easy way to cancel out functions like x. Constants, absolutely, we can tweak with constants, but if we try to correct things with adding more variables into the function, then trust me, you're going down the wrong road. You'll see as we check different examples throughout this unit.